Professor Hadas?
Yes.
Yeah. So I have made you as the host. I think.
Okay, thank you.
Project. Yeah. Yeah. Good afternoon, Hadas. Yeah.
Hello.
Yeah. Hello. Hi.
Hi. So you can hear me well, right?
Yes, I can hear you.
Okay.
You can just mute the participants. There is an option. I think Subhash.
Yes, I'll do that.
Yeah. Okay. Mute all.
Okay, so hi everyone. Today we will start a new topic, which is on advanced oxidation. So I will share my lecture. I just want to confirm that you can hear me well and that we can start, okay? Okay, so hi everyone. The topic of today would be application of nanomaterials in water treatment to enhance AOP in water, domestic and industrial based wastewater. Okay, so this is the topic of our discussion today. And I'll just go over here. When we think about the contaminants that are present in water and wastewater, we have a wide variety of contaminants, and they can include organic contaminants, inorganic chemicals, nutrients, disease-causing agents, herbicides, pesticides, personal care products, viruses, bacteria, antibiotic-resistant genes, sewage, sediment pollution, turbidity, and so on. So the list of contaminants that we can have in water are very wide. If we subdivide the contaminants into the different streams from where they come from, then we can see that with industrial waste, we have either chemical pollutants or physical pollutants, which again can be subdivided into organic compounds and inorganic compounds. So examples for organic compounds could be PCB and pesticides or biocides from the industrial waste, or inorganic compounds such as heavy metals. And then we also have physical pollutants, which is also thermal heat and oil spills. We also have agriculture runoff. And usually agriculture runoff has fertilizer and pesticide residues. And then again, we also have domestic sewage, which has also suspended solids, different types of colloidal materials that include fecal matter, bacteria, fibers, and dissolved materials such as nitrate, ammonia, and different types of salts. And also, so we can have all these type of contaminants in the water. Now, the treatment technologies that are available for pollutant removal are wide. We have the conventional methods that Dr. Birani already discussed, so we don't need to go over these methods, which include coagulation, flocculation, precipitation, filtration, adsorption to activated carbon, biodegradation. So all these are very standard conventional methods that are well known, and we have also different established recovery processes, and these can include extraction, evaporation, oxidation, electrochemical treatment, membrane separation, membrane bioreactors, ion exchange, and so on. And then we have the technologies that are considered more emerging, which can include advanced oxidation, adsorption into non-conventional materials such as nanomaterials, and you had a lecture on absorption of to nanomaterials. It could include biomass treatment through biomass, nanofiltration, and so on. So we can divide the technologies into conventional technologies that are established recovery methods and those that are emerging. When we look at wastewater treatment, we have, and this was also discussed, I'll just go over very quickly. In a wastewater treatment, in a standard treatment, we have the wastewater, then we have the pre-treated effluent, the treated effluent, the post-treated effluent, and the water discharge. Now, the first step is pre-treatment, and the pre-treatment basically includes coagulation, sedimentation, and very basic processes that are used to remove part of the total suspended solids and some of the BOD. Then we have primary treatment, which may include some type of separation and some type of sedimentation, precipitation. We have secondary treatment, which is usually, for example, activated sludge or membrane bioreactors. And then we can have tertiary treatment that includes, in many cases, for example, sand filtration and chlorine disinfection, or it could include membrane filtration, or it can include oxidation. Now, advanced oxidation sometimes is considered advanced treatment, or for example, soil aquifer treatment could be somewhere between the tertiary treatment to advanced treatment. So therefore, and we also have treatment of the residual sludge. So all of these steps are part of the process. Now, when we include advanced oxidation, usually advanced oxidation is a treatment that is on the last step of the the process, okay? So if we have, for example, removal of large solids through mesh and screen and bars, and then we have primary sedimentation, secondary treatment, and then we have maybe sand filtration and some type of disinfection, the AOP will come at the last step, okay? Now, since AOP also advanced oxidation processes, since they also improve the biodegradability of the effluent, then in some cases, there have been some studies, I would say not many, that actually post AOP, the wastewater went through biotreatment again. Since the advanced oxidation increases the biodegradability, and therefore the effluent underwent through biological treatment. So there are many places where AOP could be implemented. There's also a study that used, for example, ozonation on the raw sewage to enhance coagulation and also oxidation, but that is more like on a rare and mostly for industrial-based wastewater. So I would say that in most of the cases, the advanced oxidation process are the last process in the step. When we have residual contaminants in the waters, such as pharmaceuticals, drugs, personal care products, pesticides, herbicides, and these type of chemicals, organic chemicals that cannot be oxidized through the standard biological treatment that is not intended to remove those pollutants. Also, it depends on where the effluent, what is the next step of the effluent. For example, if it goes through agriculture, irrigation of edible crops, then there is more incentive to oxidize the pollutants. However, if it goes through agriculture irrigation of non-edible crops, or if it goes through to river or these types of treatments, or toilet flushing or Gulf irrigation or stuff like that, then there's less incentive to actually remove those pollutants and use advanced oxidation technologies. Now, AOPs are not regulated in any way. Most of the micropollutants, there's only like a few places in the world that actually mandate or have suggestions on the concentration of residual drugs, antibiotics, personal care products, and stuff like that in the effluent. But in most of the cases, there is only recommendations, and it's not mandated to treat these type of contaminants. So when we look at the quality of domestic wastewater, domestic wastewater actually can vary in its in quality, because it depends on what is the input to the domestic wastewater. Usually it can contain shower water, urine, feces, of course. But if we look at the liquid phase, it's shower water, urine, washing machine water, and it could be also other streams from industrial processes. So for example, we have guidelines that actually allow industrial wastewater following some type of pre-treatment to get connected to the wastewater stream. So to the domestic wastewater stream. So if industrial wastewater has a permit, then it could be connected. Then we have also the solid waste in the wastewater, which of course includes human feces and can include also kitchen waste. And then we have mixed with water for transport, and it can actually go to toilet flushing. And all this actually becomes domestic sewage. Now, we can quantify the amount of wastewater and estimate the amount of wastewater by multiplying the population to be served per capita and per capita sewage contribution per day. So this is the amount of sewage per day per capita multiplied by the amount of people, and therefore we can quantify the amount of wastewater. Another way to quantify the amount of wastewater is actually to multiply the water consumption by 60 to 80%, and that will actually give an estimation of the amount of domestic wastewater generated. Of course, this does not include input from the industry, okay? So if we have input from the industry towards our wastewater, then it will not, it will be added upon this. So about 60 to 80% of the water that we drink and consume, and it could be consumed by direct drinking or through food, through cooking and stuff like that, would become wastewater. Of course, there is fluctuations in the wastewater flow between the maximum and the average. So for example, maximum sewage flow are usually in morning, evening, and then at night, of course, there's like minimum flow. So there's kind of like between the max and the min, we can also multiply the amount of wastewater generated by 2 to give the maximum and by 2/3 to give the minimum. Okay. Of course, when we treat wastewater, it doesn't matter with which treatment, and we'll soon get to the nano-based AOP treatment technologies, we must follow the permissible limits or the regulations and the standards. So just to recap, our water sources can be contaminated with domestic wastewater, which can have, for example, different types of drugs, agriculture effluent, which would have pesticides, nitrates, and stuff like that, industrial wastewater, which has different types of aromatics, solvents, stuff like that, heavy metals, and also we have, for example, hospital sewage, which can have drugs. By the way, hospital sewage is not mandated in many cases as industrial-based sewage. So therefore, surprisingly, it doesn't always have to go through the same rigorous limitations as with industrial-based wastewater. You know, it's very surprising, but in many cases, this is the case. Okay, so the Central Pollution Control Board releases permissible limits for water discharge. However, the current wastewater treatment methods, they actually pose a threat to the environmental sustainability. Because for many industries, it's very difficult to follow the zero liquid discharge regulations that are required. And therefore, that, of course, and therefore that has like many impacts. But if we look at the permissible limits for wastewater discharge, then we have limits on the pH, on the chemical oxygen demand, the biochemical oxygen demand, oil and grease, fluoride, chromium, iron, manganese, total suspended solids, phenols, sulfide, and so on. So there are limits to the treatment. Therefore, any treatment that we actually adopt or adapt for treating wastewater should go through the limits, and the limits change with geography, with state, with a type of wastewater. And as I said, like, for example, in our case, industrial wastewater can actually be connected to domestic wastewater following pre-treatment, but of course it depends on the type of the industry, okay? There are also regulations and standards that allow discharge to the sea, but it very much, again, depends on the type of the industry, the type of the pre-treatment, and so on and so forth. Agriculture contamination is usually a huge issue because agriculture runoff is a non-point source, and therefore it's diffuse, and it has like many, therefore many problems and issues with regard to that. Okay, So thinking about which types of industrial wastewater we need to deal with, we have like mining industry, mechanical industry, chemical industry, food industry, manufacturing industry, and others. And this is like a list of different types of industrial waste for various sectors. Okay. So if we look at the characteristics of domestic sewage versus other types of industries, we can see, for example, that the chemical oxygen demand in domestic sewage is much lower than in different types of wastewater that come from different industries, as well as also the total and the soluble chemical oxygen demand. And also other parameters, the volatile suspended solids, alkalinity, suspended solids, total phosphorus, ammonia, the TKN. So we can see a difference between these things, but I think one of the things that actually is mostly prevalent is the COD, which in industrial wastewater in many cases is much higher compared to the COD in domestic wastewater. And therefore we can see here that the permissible limit for COD is 250 milligrams per liter, which means that after removal of most of the chemical oxygen demand, we have still residual, and the chemical oxygen demand is in milligrams per liter. The micro or nano-based pollutants that are suggested to remove are in concentration of nanogram per liter and microgram per liter. So for example, the drugs, for example, like if we talk about carbamazepine, sulfamethoxazole, all these drugs, their concentration are in microgram per liter or nanogram per liter. So their impact on the COD is very low. Therefore, we can withstand the COD of the permissible limit, but still have residual organic contaminants in our wastewater that we need to treat. Now, there are few options to treat these type of residuals, which we will talk about them very soon. Okay. Now, if we look at we'll go over this really quickly, I think because we already discussed these issues. Okay. But if we look about comparing, if we look at biological treatment versus other type of advanced oxidation processes, actually they're not competing, because usually AOP in wastewater will come after treatment. And as I said, in some cases, actually, since the AOP increases the biodegradation of the effluent, we can have a recycling stream back to the biotreatment in order to improve and reduce the BOD even further, okay? Advanced oxidation process may include, and we'll discuss this very soon more in detail, photolysis, heterogeneous and homogeneous, photocatalytic reactions, non-catalytic oxidation, blah, blah, supercritical wire gasification. So they're very processes that generate reactive species. These are emerging processes and disruptive processes. Compared to sorption, sorption is actually a technology that actually is a phase transfer technology. So sorption will take the micropollutants and the residual organic matter from one phase to the other, usually from the liquid phase to the solid phase. However, AOP is considered destructive technology, okay? We have advantages. One of the advantages is in situ production of reactive oxygen species. It has little consumption of chemicals or even none. It is possible to mineralize the pollutants, but it's not very likely, because usually by itself it will not mineralize. But if we combine AOP with a biofilter, for example, and this is a pilot that we had in one of the wastewaters, where we combined ozonation-based AOP with a high rate biofilter, then actually the AOP biodegraded, the AOP oxidized the micropollutants, and then the biofilter kind of finished the process. So actually we had post AOP biofilter, we didn't have any residual pollutants left. An advantage is no production of sludge compared to sorption where we have production of sludge. Rapid degradation, it's very efficient for recalcitrant molecules such as dyes, for example. And it's good in removing the COD and the TOD, and it can convert insoluble organic matter into simpler soluble compounds. However, it does have disadvantages. In many cases, and most of the publications, as I said before, they're only lab scale. So many people publish tons of papers that I honestly don't see where they're going at, with different types of AOP based technologies, but no implementation. It only stays in the lab scale. So it may be economically not viable for small industries, okay? Again, it depends because there are changes in the viability and the economic options for using AOP. It may have technical constraints. So for example, if we require an ozone generator or stuff like that, it may be technically constraining. There may be a formation of byproducts because we oxidize the pollutants. If we do not oxidize them to carbon dioxide and water, we will have residual byproducts left in the system. For example, and these byproducts in some cases may be more toxic than the parent compound. In some cases, it will require high pressure or maybe energy intensive, okay? Now, nanomaterials in water treatment can be used in many cases, and we already discussed in the nanomaterials, they have a high surface area and stuff like that. They can have good performance, they can be multifunctional. However, recent advances in nanotechnology can offer leapfrogging opportunities to develop the next generation water supply systems. However, it is not sufficient to design a smart nanocatalyst, okay? If it's not combined with a smart reactor and we cannot use it in practice, then there's no point. And one of the huge challenges, like in many studies, and I can say, for example, in studies that we did in the lab, that, for example, we designed MOF, which is metal organic framework. This MOF was really good in absorbing arsenic. We did a literature survey to test all the different sorption materials based MOF. Some of them actually work in pH 2 at high temperature and pressures. So that is not practical. If we want to design something that would be practical for environmental use, we need to have the technology working at pH between 7 to 8. We need to have normal temperatures. We need to, for example, to have raw materials that are not very expensive. And in addition to that, we need to actually find a way to work with the nanoparticles, not in the nanoparticulate way. So for example, we designed from the MOF, we designed granules, and these granules, we added them to a filter, okay? And the hydraulic residence time of the process should be very short. So when we did the literature survey, we saw papers that showed really good sorption of, for example, arsenic, but it took them hours. When do we have hours as a residence time in a filter in actual practice? It's not practical. So therefore, like, for example, when we design things, we sometimes pay with efficiency, but at least we try to do things in a way that would be environmentally relevant. So with hydraulic residence time, with raw materials, with, of course, it must be on some type of support, and it should be efficient at a very short time. And with normal temperature, pressures, and pH, and also work with natural water. So not only test with I don't know, DI water or water with some type of buffer. It should work with water that has other constituents inside. And also particles may be colloid. So because if before the sorption technology, we don't have like a UF filter, then maybe we'll have colloids in the water, and that will also impact our technology. So in technology design, as environmental engineers, it's very important for us to emphasize all these factors, okay? So our current water treatment, distribution, discharge practices are heavily rely on conveyance of centralized system. Centralized systems are not relevant in many cases because they require distribution systems and collection systems. And it's not the case in many places, not relevant. And this is the place where nanotechnology can actually be efficient. It could be efficient in small scales, decentralized systems that are in remote locations, and that could be rely maybe on activation using solar sun and stuff like that. So nanotechnology actually can take place in the small scale, decentralized systems, especially if it's also for intermittent water flows and also for cases where we have intermittent energy, okay? And therefore, highly efficient modular and multifunctional processes enable nanotechnology to provide high performance, affordable water and wastewater treatment solutions that less rely on large infrastructures. But as I said, we need to design the treatment to fit local constraints. We cannot separate as scientists the publications from reality. But if you scan most of the papers that did tons of studies on photocatalysis and catalysis and all types of different types of AOPs, they are totally not relevant to work. Well, maybe it's good because, you know, it's more papers, okay? So as scientists, we need to show that we publish, but they don't impact the environment in any way. They're just published and maybe a few people will read it. So this is kind of like a criticism and where we really need to take things to the next step. And I think we have enough body of knowledge to not think always of designing the new material, but to take the current materials to the next step. Okay, so when we look at nanotechnology in water treatment, okay, we already discussed it. We have the organic nanoparticles, polymer-based nanoparticles, and inorganic nanoparticles. Now, this nanotechnology can actually be implemented in various ways, in nanomembrane filtration, in disinfection, in Fenton reactions, in adsorption, and photocatalysis. So nanotechnology for water treatment has a huge potential. Again, if we take it to the next stage, the next level of implementation. Okay, and the fabrication of nanomaterials to enhance advanced oxidation processes in water treatment could relate to usually to nanophotocatalysis, okay? However, nanomaterials in general, as just a recap from the previous slide, could be used also as a disinfectant in nanofiltration processes and nanoabsorption. So we can actually use nanomaterials in all these different processes. Now, I read a study that tried to find what are the most prevalent keywords in publications related to advanced oxidation and water and wastewater treatment. So the most prevalent keywords, of course, is advanced oxidation, wastewater treatment, oxidation, hydrogen peroxide, wastewater degradation, ozone. Now, if we look here and we find photocatalysis, so we see that ozonation and photocatalysis are smaller in size, which means they're less prevalent for wastewater reuse. We have your UV radiation, biodegradation, catalysis, iron in some cases. Here we have again advanced reduction reactions, advanced oxidation, reaction kinetics, What I don't see is pilot studies. So most of the papers that, that worked on AOP and wastewater treatment, they stay in the lab with controlled conditions, which makes it very convenient and easy, of course, but that is the case, and this is the reality. Okay, so this is definitely something that we should think about, okay? Now, the nano-based AOP for wastewater treatment. So the current research in wastewater treatments with AOPs is mainly focused on a pilot scale, maybe, but usually in batch mode. The evaluation in real conditions in continuous flow mode is mandatory for implementation. Fenton processes have widely been studied, but its application on wastewater, such as tertiary treatments in real conditions, is restricted since the optimal pH 2.8. What's the point? What's the point of studying Fenton reactions in wastewater effluent? Just pointless. We will never reduce the pH of the wastewater to pH 2.8 unless it's a specific industrial-based wastewater that already the pH is at that pH. But if not, then what's the point? The most frequent catalyst is titanium dioxide. However, the recycling and the recovery of these suspended TiO2 particles become cumbersome and expensive, making the use of suspended systems not viable. Therefore, if the research studies stay with suspended particles, then again, how can we apply it? As an alternative, new systems have been developed using immobilized catalysts. Of course, when we immobilize the catalyst, we reduce the efficiency of the process. Of course, when we test with real water that has also colloids, organic matter, viruses, whatever, we will reduce the efficiency. But we need to test the efficiency in real conditions to understand if this new synthesis is actually relevant. And if not, then keep on trying again and again to find something that can actually benefit society and make an impact. Okay, so nanomaterials to enhance advanced oxidation processes in water. As I said before, AOPs are highly impacted by the quality of water, as many other technologies, by the way. So it's very important, of course, to understand the types of the water, whether it's domestic or industrial, and what is the next step? Where is the water going to? So when we design a technology, we must understand the entire loop. Is it used water discharged from residential? Does it contain organic and inorganic solids, microorganisms? What is its composition? And of course, we need to understand where it's going to. Okay, so it's very important when we deal with AOP to understand, do we plan to reuse the treated effluent in some case? Okay, so now let's go to AOP, because just I gave a very long introduction on what is required from an AOP, but now we need to understand what AOP is. So AOP is basically an array of chemical processes used to oxidize or mineralize organic pollutants in water by the accelerated production of hydroxyl-free radical. The dot shows the outer electron orbital, which has an unpaired electron, reactions with double bonds or extracting hydrogen atoms. And in many cases, the AOPs are done in ambient temperature and pressure. So the AOP radicals are very effective in destroying organic chemicals because they are reactive, and they also prefer electrons, okay? And they react rapidly and non-selectively. So one of the things with AOPs is that they're not selective. So they would oxidize many organic compounds that are electron rich. Okay, so this is something to understand, that it's not selective. It's an advantage and it could be a disadvantage. So it really depends. Moreover, the second order rate constant of hydroxyl radicals with organic chemicals is in the order of 10 to the 8 to 10 to the 9 liter per mole per second, which is almost a diffusion-based limit. So therefore, it's very important, the design of the reactor using advanced oxidation processes. Okay, so this is something that is very important to consider. So I think these are the main points to consider. The hydroxyl radical formation could be done with a combination of different technologies. So for example, we can combine ozone or ozone with hydrogen peroxide, which is termed peroxide, UV and hydrogen peroxide or UV peroxide, UV and chlorine, UV, ozone, hydrogen peroxide. For example, we can have TiO2 catalyzed UV and phenton reactors. But again, we always must ask the bottom line, are these technologies practical? Are they sustainable? And are they economic? Okay, so these are things that we actually must ask ourselves. The type of different oxidants, we can see that the hydroxyl radicals has one of the highest oxidation potential, which shows its potential in oxidizing organic contaminants. Reactive oxygen species in general are any type of ROS, which includes alkoxy radicals, singlet oxygen, hydroxyl radicals, hydroxide ion, hydrogen peroxide, superoxide radical, and peroxy radical. So it actually relates to all the oxygen-based reactive species. And these are the ROS. Free radical formation may be initiated by a combination of photolysis, ozone, hydrogen peroxide, sonolysis, and stuff like that. And again, the rate of the oxidation depends on the concentration of the initiating species, the pH, the pollutant concentration, the temperature, ion, and scavengers. So in the water, we have many types of scavengers. The scavengers could be, for example, carbonates. So we have in the water carbonates. The carbonates can scavenge hydroxyl radicals, natural organic matter, chloride. So we have many types of scavengers in the water that could actually scavenge the hydroxyl radicals. Now, when these hydroxyl radicals are scavenged, they can undergo either initiation or termination. So they can actually initiate a chain reaction. So for example, the hydroxyl radical can react with natural organic matter, form an organic radical. So this is initiation of more radical-based processes. However, for example, on the other hand, hydroxyl radical can react with a different type of organic matter, which will scavenge it and will not initiate any further reactions. So therefore, we can have either initiation or termination, and it really depends on the type of the organic matter. So which makes it really complex, because with different types of wastewater, we have different types of organic matter, and it's very difficult to predict what will happen. Okay, so this is something also to consider. And again, these are, we discussed this, the different types of reactive species generated. Okay, so when we think about hydroxyl radicals, just to make a summary, it's extremely reactive. It's very short-lived. It's not selective and has a very low steady state concentration between 10 to the minus 12 to 10 to the minus 13 molars. Now, a question that is raised, is it really a sustainable and green technology? That's a question to be asked. When we subdivide the different advanced oxidation processes, we have irradiation. So we can subdivide AOPs to different types of classifications, and it really depends. So I like to classify according to radiation, because maybe I'm like, my expertise is UV radiation. We can subdivide it to radiation-based processes such as photolysis and photocatalysis. And we can subdivide it to non-irradiation-based processes such as phantom, electrochemical, electrical discharge, ozonation, sonolysis, wet air oxidation. However, a huge advantage is if we can post biotreatment following the AOP. And therefore, this will allow clearing of the waste. It could be any type of biotreatment. So it could be suspended biotreatment. It could be biofilters. It could be even BAC, which is biological activated carbon. Okay, so any type of treatment that has post-biotreatment following the AOP has a huge advantage because the AOP, as I said, it increases the biodegradability of all the residual and recalcitrant organic matter in the effluent. Now, one of the really small, really important thing to consider with AOPs is the type of irradiation. This is something that in many cases is undermined. So we really need to understand which type of source of photons can we use and what are the most practical ones. Today, there's a new class of UV visible based radiation source, which are called light emitting diodes, LEDs. We've been working on LEDs in my lab in the past 5 years. And LEDs are really beautiful. And this is because the UV-based LEDs, they come at different wavelengths, so we can target the wavelength that we want. So we can target, for example, 265 nanometers, 275, 280, 285, 290, 300, 365, 385, 395, 405. So we can actually, for example, photocatalysis, we can match between the band gap and the LED, which is a beautiful technology. Now, looking at the LED-based technologies, of course, there are many things to understand. We need to understand how to quantify the photons, and we need to understand, for example, how to design them in a smart reactor. Because LEDs are very small, so they can be combined in many, in various ways, and they're different than the mercury-based lamps. And so it's kind of like, and the cost is reducing. Due to the Corona crisis, as we all know, where people wanted to disinfect every place in the world, the LED industry, the UV LED industry really boomed. And now the cost is lower, and it's expected that by 2025, it will be a huge industry, and the cost would be even lower. So that's a huge advantage. And the LEDs can be used also for this direct photolysis for disinfection, but they can also be used for photocatalysis. We now have a project, a huge project, where we're designing metal-based membranes that are, I think I told you about this, that are coated with EPD system compared to ceramic-based membranes. And we're now designing a smart reactor that combines the LEDs with filtration through photocatalytic membrane reactors. Of course, in these cases, we must target the catalyst to be to absorb in the UVA visible range in order to reduce the cost of the LEDs, because the UVC LED range, and if we look here at the electromagnetic spectrum, the UVC LED range is up to about 285 nanometers. They're more expensive. But if we can target, for example, in the 285 till the 320 are less expensive, and then the 320 nanometers until the visible range, 400 nanometers, are even less expensive. So if we can target a photocatalyst that would be activated, for example, with UVA vis wavelengths, then the combination with LEDs makes it really interesting to apply. Okay. So how can AOPs be used to enhance water treatment? Advanced photocatalytic oxidation, if we think about that, is a new innovative advanced wastewater treatment technology. It's highly effective and could be potentially environmental friendly. It could also be used for effluent of industry that has a mixture of suspended, dissolved, and inorganic pollutants. But of course, as I said before, prior to the AOP process, we need to actually remove the residual particles. It can also be non-hazardous. But of course, we need to target the process to fit the needs. And it could also make the wastewater more biodegradable. AOPs can also be used for industrial wastewater, not only for domestic type of wastewater. And AOPs can treat different contaminants, and this is, of course, just a very short list. Okay, I'll go on here. Okay, so if we look a little bit about equations, calculation of the steady state hydroxyl radical concentration is very complex. Okay, it's not an easy thing. So, for example, if we want to examine the degradation of the target organic compound, which is a CR, so the degradation over time is minus the second order rate constant for the destruction of R together with hydroxyl radicals, multiplied by the concentration, the steady state concentration of hydroxyl radicals and the concentration of the target organic compound. Now, the steady state concentration of hydroxyl radicals is very difficult to quantify. We do that in the lab, for example, with a target chemical that is called PCBA. PCBA actually is, for example, a target pollutant that we add to the solution while exposing it to the different photocatalytic reactions or different photolysis or different types of AOP reactions. And it has a known rate constant. Okay, so it has a known rate constant, and therefore we only need to measure the concentration of PCBA before and after, and that's how we can actually back calculate the hydroxyl radical steady state concentration. Okay, of course, this is only in completely mixed systems when we know that we generate steady state concentration of hydroxyl radicals. This system, it's much more complex to measure when we do not have completely mixed systems. And we can also calculate the scavenging potential of the water. The scavenging potential of the water relates to the type of effluent or the type of water. So the scavenging potential can relate to different groundwater, surface water, effluent, and stuff like that, okay? And if we look at the different rate constants, so I mean, it's a long table, I will not go over it. But we have, we can actually, there are no numbers for the rate constants of hydroxyl radicals with different compounds. Okay. We'll stop at this slide and then we'll have a short break. Just to summarize, advanced oxidation processes could be quantified could be actually characterized in different ways. So I showed you, for example, classification with photolytic and non-photolytic processes. But AOPs can also be classified to homogeneous and heterogeneous, okay? If we classify AOPs to homogeneous and heterogeneous, then we can further classify to photochemical and chemical. So chemical would be, for example, ozone with hydrogen peroxide, ozone at basic conditions. So ozonation at basic conditions mostly imposes hydroxyl radicals, whereas ozonation at acidic conditions will mostly impose a direct ozonation and not the indirect reaction through the generation of hydroxyl radicals. We can have all these processes, and we can have all these photochemical processes, which are basically homogeneous processes based on UV photons. So we can UV combined with ozone, UV with hydrogen peroxide, UV with ozone and hydrogen peroxide, UV in sonolysis, photophantom, and microwave ozone. So all of these are photochemical-based processes. Then we can have the heterogeneous processes, which include the photochemical and the chemical. The photochemical are actually those that are combined with the nanotechnologies. Okay, for example, with titanium dioxide or different types of nanoparticles. And the chemicals are these, okay? And all these are called advanced oxidation. And then we also have advanced reduction processes, which are less relevant. So if we think where nanotechnology can be combined with AOP, it's only in this stream. So it's the stream of heterogeneous phase and the photochemical. So this is where nanotechnology can be combined with advanced oxidation, okay? Of course, we can also combine, also add to the system ozone or hydrogen peroxide together with a catalyst. And that will also serve as a photocatalytical based heterogeneous phase AOP process, okay? So the next lecture, we will dive deep into this section, okay? Does anyone have a question, or do you want to have a break? Okay, so let's say that we'll have exactly a 10-minute break. And please, so 10 minutes from now, we'll be starting. Because I have a different time, like the time now is 3:25, right? Am I correct? Okay, good. I had to translate from my time zone. So it's 3:25. And you have a 10-minute break, which means that you return back at 3:35, right? Okay, so good. I did a quick calculation. I did it. Okay, good. So I'm looking forward to see you at 3:35. Okay, thank you. Hi, everyone. So we will return back to the lecture. Okay. So we'll quickly scan over various types of AOP. I just want to know that you can hear me well. If you can write in the chat, so I just know that everything is okay. Okay. Okay, good. So can you see the presentation? You can hear me? Okay, so I assume that I can move on. So there are different types of AOPs. One example of AOP is AOP based on ozonation, where we can have here different types of processes. So this is the ozone molecule. Ozone with natural organic matter in the effluent can actually result in formation of hydroxyl radicals, but we can also add energy to that. We can add hydrogen peroxide. We can target the direct oxidation of organic pollutants at, for example, acidic pH, or target the indirect reaction by either having basic pH or adding hydrogen peroxide, or actually adding UV radiation. And this is the ozonation process. We can also have Fenton reactions where we actually oxidize Fe2, and we actually with the help of hydrogen peroxide, and generate the hydroxyl radicals. We can recycle back the process using a UV source. And that way the process is actually can continue, okay, in a recycled way, and therefore we can have the process continuing through the regeneration back of RN2, okay? Then another type of AOP could be UV-based AOP. Within this process, the UV will photolyze hydrogen peroxide and form hydroxyl radicals. And these hydroxyl radicals can actually do many things. They can oxidize, if it's bacteria, they can oxidize the membranes, the proteins, the lipids, but also they can oxidize various organic pollutants. Now, one of the key factors in these light-based processes is, of course, the radiation intensity and also the radiation wavelength, okay? The water temperature, the turbidity of the water alkalinity, the pH of the water. If we have, for example, iron in the water, so all these parameters are the carbonate system, I said alkalinity. So all these parameters are very critical for the success of AOP processes. Okay, so therefore we can divide AOP to photocatalytic and catalytic processes. Actually, the term photocatalytic is a combination of two words. Photo, which is of course related to photon, and a catalyst, which is a substance that actually alters the reaction rate upon its presence, but a catalyst is not consumed by itself, okay? So it only catalyzes the process. Therefore, photocatalysts are materials that can change the rate of the chemical reaction when they're exposed to light. So this is what we want to have from photocatalysis. The photocatalysis induces a reaction by using light and a semiconductor. And we'll go over a list of different types of semiconductors that they absorb the light. Most of the photocatalytic processes usually have low efficiency. And therefore, part of the low efficiency can result to the interaction of light with a photocatalyst. It could be due to reflection. It could be due to physical processes such as reflection and scattering, but it could be also due to recombination processes. The key advantage of photocatalysis compared to other types of AOPs is that we don't need to add any chemicals. So if we compare different types of AOPs compared to ozonation or compared to hydrogen peroxide, with hydrogen peroxide, we need to add chemicals. With ozonation, we need to add chemicals. But with photocatalytic systems, we don't need to add chemicals to the process. In many cases, the supply chain is very critical, okay? So there are issues with supply chain of chemicals. Ozonation, for example, need to be generated on site. Hydrogen peroxide is very problematic to store. We need to add a stabilizer to the hydrogen peroxide, otherwise it will degrade really quickly. Hydrogen peroxide in the industry is not at the same concentration like we use in the lab. So in the lab, we use 35% that has also a stabilizer. In the industry, usually we use lower concentrations of hydrogen peroxide. And also this chemical must be, it's a dangerous chemical, so it needs to have all the safety considerations within it, okay? And high temperature, of course, is really problematic with the stability of hydrogen peroxide. Ozonation must be generated on site. So when we generate ozone, for example, we need to have we need to take air, we need to separate the nitrogen from the air. Then we take only the oxygen. It goes through a generator. The generator produces a stream of combined ozone and oxygen stream. And this gas stream, which at maximum would be 14% ozone, will be actually introduced into the liquid. So we have a gas-liquid interface, and therefore it's very important to actually control the way that we introduce the gas into the liquid. And if we have wastewater and we have particles, then we also have gas, liquid, and solid particles. So we have a three-phase phenomena, which is very difficult to model. And therefore, usually our knowledge comes from empiric reactions. Same with also with photocatalysis. So all these things actually make the AOP processes, the design of the process is very important. Not only the process, but also smart design of the reaction. So I think we already spoke about this. Catalysts, as said before, they can make reactions possible under achievable conditions. They can generate high yields of product. They can reduce the amount of side products and waste created. And they can make a chemical process greener, okay? So upon correct design, the process can actually be greener, and that is, of course, an advantage. When we look at the different metals that could be used for photocatalysis, we actually look at the transition metals, okay? That we can use for using some of the transition metals can be used as a catalyst. These transition metals, could be very useful in oxidation reduction reactions because of their outer electrons, and especially susceptible to oxidation and reduction. If an oxidized transition metal actually interacts with a molecule, it can take electrons from that molecule, which will be then oxidized. If a reduced transition metal runs into a molecule, it can actually give electrons and reduce it. And I think because the transition metals are easier to oxidize and reduce than other elements, then the process can go actually faster. Okay, we can go over this. One of the key issues with using catalysts is actually we want of course to have particles that have high surface area, but then we need to facilitate phase separation. Therefore, one of the things that are required is actually to load the catalyst onto different supports. The common supports that the catalyst can be loaded on would be activated carbon, alumina, or silica. The supports, however, can have an indirect effect on the activity and the selectivity of the process. And therefore, the choice of the support is very critical. I think we kind of discussed this with Fenton reactors. The operational parameters would be low pH. If the pH is high, then we'll have precipitate forming, so that would not be efficient. And of course, the process is governed by the ratio between the Rn and the hydrogen peroxide. However, we can create hydroxyl radicals, and these hydroxyl radicals can actually use for oxidizing the pollutants indirectly. And therefore, this process can has some advantages because it uses lower cost raw materials, but also has disadvantages. Okay, let's move on here. Okay. So as we discussed the semiconductor material upon exposure to UV or visible light. So today there is a trend of designing photocatalysts that can be activated with UVA visible light. Can provide the surface reaction, can provide the surface areas where redox reactions can occur. Okay. So this is basically the process. Now the process, if we look at the different pollutants removed, for example, by doped titanium dioxide, doping agents could be various doping agents. And the idea of doping the catalyst is that we can also use higher wavelengths, which are of course less expensive. So we can dope titanium dioxide and move from 365 nanometer even to the visible range, okay? And therefore we can see that with many doped nanophotocatalysts, we can use a visible light source or sunlight, okay? So this is also very important. I think we discussed this, okay. So we can use various semiconductors such as titanium dioxide, zinc oxide, and so on. Why should we use a photocatalyst? Because it actually converts a solar light into chemical reactions. And the first step in the photocatalytic mechanism is light irradiation, okay? So the catalyst will absorb the light. And of course, the wavelength of light equals to the Planck constant multiplied by the speed of light divided by the band gap, okay? And so the first step would be light absorption. The next step would be electron sensitization and generation of the electron hole pair. So we can see here, if we look here, we can absorb light and then we can generate the electron hole pair. The next step would be migration of the electron hole pair to the surface of the catalyst. So we see here migration of the electrons and the holes to the surface of the catalyst. However, we want to avoid or minimize the recombination. The next step would be reaction with electron donors or electron acceptors. So either reacting with oxygen to form superoxide radicals, or reacting with water or a base to form the hydroxyl radicals. So that would be the fourth step. The influencing parameters are numerous, are the light intensity, the oxygen concentration, the pH, the concentration of the target contaminant, concentration of the catalyst in the water matrix. So therefore, it's a very complex system. One important thing, as I said before, it's to coat the particles onto a support. So this is an example of a coated glass. Two major drawbacks of photocatalysis is a recombination of the photo-generated charge carriers and possibly a wide band gap. So in order to improve a solar light-based photocatalysis, we can either modify titanium dioxide by doping it, for example, with nitrogen, or induce morphological modifications, or couple with other semiconductors, or develop other based photocatalysis, for example, as bismuth-based photocatalysis and others. Okay. So the doping process intentionally induces impurities, defects into the semiconductor in order to modulate its electrical properties. And then we can also design Ti2 heterojunctions in order to improve the light harvesting and reduce the recombination. Another important feature, as I said before, is to immobilize the photocatalyst. We can immobilize the photocatalyst onto different supports. For example, conventional membrane is only a physical process, but we can combine the membrane with a photocatalyst that will be activated by light. Of course, one important feature is that the membrane by itself would not be degraded by light. Therefore, the photocatalysis coating with a catalyst should be, for example, on ceramic membranes or like metal foam membranes or different types of carbon-based membranes. However, upon coating polymers, polymeric-based membranes, of course, there's an issue of degradation of the polymeric-based membranes, unless it is done in a way that that the catalyst will absorb only visible photons, and maybe in that way we'll have less degradation of these polymer-based membranes. It's also very important to degrade the organic pollutants, to inactivate microorganisms, and design a membrane that will have a self-anti-biofouling action. So we need to actually look at all these parameters. In addition to that, with photocatalysis, if it's based on solar radiation, it's really important the choice of the solar photoreactor. So, for example, here in Switzerland, they designed a CPC type of reactor, and here in this image we have a parabolic through a concentrator. So the choice of the solar reactor is also very important upon photocatalysis. Okay. And to summarize the photocatalysis, absorption of photons with energy greater than the optical band gap, electron promoted from valence to the conduction band, electron and hole formed and migrate to the surface. Hydroxyl radicals attack most of the organic contaminants. They transfer the organic contaminants and micropollutants to simpler, harmless organic molecules that are eventually mineralized. And as I said before, if we want to eventually mineralize the photocatalyst, then it would be advantage if we combine it either with sorption or some type of biodegradation process like a biofilter, biological activated carbon, or even some type of suspended biotreatment. I would like to introduce a paper that we published on ceramic-based photocatalytic membrane reactors for water treatment. Where to next? And the idea that we published this paper is that we actually scanned the entire literature because we wanted to know what would be the next step, because there are many papers that publish different types of photocatalysts. And as I said, I'm not a material engineer, but I'm an environmental engineer. And that's why it's very important that we work together, that chemists or material engineers work together with environmental engineers, because we need to get to the next stage of taking smart materials into smart reactor design. Okay, so ceramic-based photocatalytic membrane reactors are becoming increasingly popular among researchers and will be soon seen in water wastewater treatment market, hopefully. This review actually that we did analysis on the ceramic-based photocatalytic membrane reactors that were fabricated today based on the different coating method, different supports, coating materials, membrane design, pore size, and model compound used to evaluate process efficiency, and the solar light source. So we actually sectioned all the different publications that used into different categories. It was like very difficult work that we did here. While all the studies describe ceramic-based photocatalytic membrane reactors in great detail, over half do not provide any information about their performance, which is very surprising. The rest use various dyes that can be conveniently detected by a spectrophotometer, or micropollutants that require analytical equipment available in specialized labs. So actually most of the papers that that described Aop-based photocatalytic processes, they actually use dyes, which of course do not represent in any way water or wastewater, or they used micropollutants, but they had, of course, an HPLC or UPC in the lab where they could analyze the micropollutants. So the ceramic-based photocatalytic membrane reactors are viewed as a convenient way to incorporating a photocatalyst into an inert surface, assuming that the surface itself, the membrane, does not participate in the treatment process, obviously. A unified test for evaluating photocatalytic membrane reactor performance should be developed and implemented for all type of studies to have potential for commercialization, of course. There is a need for standardized ceramic-based PMR testing. Only then we can know the true performance and compare between different publications or results from the literature. In order to evaluate and compare such testing, will also answer the question whether the CPMR membrane is indeed an inert support or an active part of the treatment process. So therefore, we really wanted to know what's happening, to subsection the different publications, to divide them to different types of coating materials, different type of coating processes, different types of supports, which light was used, and not only which light was used, but also most of the studies, even if they provided the power of the, like which lamps. So for example, if they use the UV lamp, they would say, we use like a 40-watt lamp, but they didn't have any measurements of the incident irradiance. They didn't have any measurements of quantifying the amount of photons that are used for the degradation process. Most of them used methylene blue, rhodamine, and stuff like that. So these compounds, and less used micropollutants. And even those that use micropollutants, there is not a unified pollutant that is used across various papers. It's very difficult to compare. We really try to spend months on trying to compare the different papers, and was extremely complex to understand how to go next, because it's very difficult to go next if we don't have some type of unified method that will allow us to reach the next step, okay? So these are things that are very important to understand. So I would like to share just a study that we did on photocatalytic membranes. This was an European Union based project. We had multiple groups working on this, both from the academics and the industry. And what we try to do is to develop a water treatment system that combines solar photocatalysis with membrane filtration. So the idea was to use ceramic membrane. And because we wanted the process to be low cost, we did not design our own ceramic membrane. We just purchased ceramic membranes from the industry. Actually, we looked for the lowest cost membranes that we can purchase, ceramic membranes that we can purchase, because we wanted to make the process affordable. We coated the ceramic membrane with N-doped titanium dioxide, and with various types of coating methods. So we had, this project was collaborated with many groups, and each group had an expertise with a different coating technology. So there was like nanojet, electrospin, plasma, sol gel, whatever. So each group took the same ceramic membrane and coated it with different coating methods. All of the groups analyzed the membranes for the coat percentage and all the different analytical measures that were done. We used a solar simulator in order to activate the catalyst. The solar simulator was an ASTM solar simulator that actually simulates solar light at 12 noon at a certain place, and that is according to the standards. The water flow was bottom up. So the water was filtered through the ceramic membrane, and then we generated a thin film of water after removing the particles with ceramic-based, alumina-based membranes as a substrate. And we had all these different goals in mind. We modified the titanium dioxide by nitrogen doping, and it increased the photocatalytic oxidation rate. So we had a 50% increase in the rate, 25% increase is by the visible light. The photocatalytic membrane reactor has multiple functions, also for filtration and photocatalysis. So these are the different functions. This is the solar simulator that we had in the lab, and we designed also a small scale system where we can either test dead end or cross flow. We had a 300 watt xenon lamp solar simulator. And we used ceramic membranes that with a 200 and 800 nanometer nominal pore size. And we used carbamazepine and MS2 bacteriophage as our model pollutants, okay? So basically, we had here the water feed, and the water feed went through the membrane. We generated a thin film, and the permeate was recycled back to the water feed, and that's how the process was. We recycled the process. We controlled the many parameters. For example, we could add compressed air if we wanted to. We could also test flow only on the surface, through the membrane, and stuff like that. So we tested different conditions. Carbamazepine was when the initial concentration, 1 ppm, pH 7. We tested different flows. The experimental time was 2 hours, but the actual time that the catalyst was exposed to light was much, much lower. And then we tested carbamazepine degradation rate constant. And what we found is that when the water flows through the membrane compared to generating a flat thin film, we get a much higher degradation rate constant. So therefore, we understood that it's much more advantageous if we actually stream the water through the membrane and not only on top of the membrane, okay? And this happened both with the 800 nanometer membrane and the 200 nanometer membrane. So we actually had efficient solar utilization, improved mass transfer, and higher surface area. Then we wanted to test the impact of different water constituents on the degradation. And because it's a light-based degradation, of course, we must have a control in the dark, okay? We used MS2 bacteriophage, which is a virus that is very similar to polio and hepatitis virus. It has a 25 nanometer in size, and it has an RNA as its nucleic acid. It's very resistant to chlorine and UV radiation, and therefore we wanted to understand its inactivation upon photocatalysis. It's resistant to UV radiation in the UVA visible range, of course. And so what we did is we tested the photocatalysis in pH 6, pH 7, pH 8.5. We added magnesium, we added calcium, and we took also surface water. What we found is that when we took water that had surface water, all the viruses, most of the viruses disappeared even in dark conditions. So therefore, in dark conditions, the viruses were just absorbed to the surface. And this shows why it's really critical to test photocatalysis in real water. Because when we just modified the pH, the photocatalyst worked really good. We almost did not have any dark sorption. When we added magnesium, we also did not have almost any dark sorption. When we added calcium to the pH 8.5 solution, all the viruses disappeared in the dark, and the same with the surface water. So therefore, we kind of assumed that calcium had a role in sorption and not necessarily in photodegradation. Therefore, we did additional tests with calcium at different concentration to understand what's happening between the photocatalyst and the viruses. The next step was to actually design a system. So we took this lab system, and we took all the operational and engineering-based parameters to design a pilot system The pilot system was operated in Jordan for gray water contaminated tap water, and also in South Africa for surface water from rural areas. Of course, one of the key issues when we used AOP-based processes is to use pre-filtration to reduce fouling on the photocatalytic membranes. Also, in addition to that, we tested many options for cleaning the membranes in order to regenerate the photocatalyst. So when we work in the lab and we're not opposed to colloids in the water and things like that, we might assume that our process is efficient. But we must consider chemical fouling, biofouling, and inorganic fouling in any process that we design. Therefore, any reactor should be operated for a very long time in order to have enough time to understand the fouling phenomena and to solve them and to decrease or control the fouling, okay? So biofouling, organic fouling, inorganic fouling, all these can occur on the photocatalytic membranes. And remember, using nanoparticles in water is not an option. It's banned in most places in the world. So designing a photocatalyst in water without actually attaching it to a support is of course very problematic. So these are our ceramic membranes. These are ceramic membranes. And we designed a system where the water streams through the membranes. The ceramic membranes are inclined in order to absorb most of the UV light, most of the solar light. And what happened within this project is that we did not reach the efficiencies that we aimed for. I'll just stop share. Okay, we did not reach the efficiencies that we aimed for. And one of the reasons is that we didn't leave enough time for testing the pilot in this project. It was a 3-year project, and material engineers generated many formulations and many coating methods, and we had many trials and errors to find which coating method was the best. We published also papers on it. We found that actually the most simple coating method, which was actually either a sol gel by dipping the membrane or by pipetting, was mostly efficient. And that is because this method also coated the inner pores. Now, because we used a membrane that was tortious, light also probably generated reactions within the pores. And because of the flow of the water through the pores and the interaction between laminar and turbulent conditions and coating and inside coating of the pores, we actually received good efficiency. But in reality, when we tested the system in the field, we had problems with fouling. When we saw that we had problems with fouling, we kind of thought what we can do to solve the fouling issue. We added another pre-filtration process, and that improved somewhat the process. Yeah, but it was very complex because it was complex to design the system. It was complex to implement pilots. It's very complex, and also the results were not as what we wished for. Now we are continuing a similar research, and hopefully And our goal is to get fast. Our goal is to design the engineering. So we're using a different type of a catalyst. We're using metal foam catalyst as our support. We're coating it with different types of nanomaterials. Also organic based, not only metallic based, and also combination composites. And we're also activating the system using LED light. And we're now designing also the pilot stage, and hopefully, hopefully the results would be better. Okay, so this is about kind of what I wanted to say about this topic. So I'm open to questions, and also just one thing is that I asked the material engineer to respond to all your questions yesterday from the chat. So I'll just read the answers. One of the questions for the chat was about silver nanoparticles. So the silver ion technology is reliable provided that careful recycling of the silver after discharge. Nanocomposite containing silver still releases metal ions over time, which lead to toxicity. Analysis of the metal ion in the composite is challenging, require multi-step processes. Mostly ICP would be useful. So I think it's basically also what we said. There are no significant research proving biodegradability affected by nanoclusters. We can use ferrocarbon composite, but recyclability is an important parameter. Nano silver wash and resuspending is challenging. It depends on the nature of the contaminants absorbed to the silver nanoparticles. We can do solvent wash would be most appropriate. So I think we also discussed the issue of using solvent wash. And again, toxicity in drinking water should be analyzed by ICP-MS for analyzing the metal ions. So it's basically also what we said yesterday. So just wondering if anyone has any remarks, questions. Okay, let me see. Okay. So sorry?
Yes, ma'am. Am I audible?
Yeah.
Ma'am, I want to know about the point that which type of nanomaterials are best for treatment of water with heavy metals?
So do you mean treatment for absorption or for photocatalysis?
Adsorption.
Oh, okay. I don't know how to answer which is best because it depends also on the type of the metal contamination. So for example, we use now for arsenic adsorption, we used metal organic framework. Again, I'm not a material engineer. For absorption of arsenic. And we actually now used also metal organic framework that we also coated onto membrane support, and also we generate granules. It's based on fuluric acid, but I cannot say like which is most efficient. I think it depends on the contaminant and on the water quality. And I don't know if someone has here an answer, then please share your response.
Please share your response.
नहीं आया आंसर इसे बोल दी कुछ और हेलो ma'am. Yes, ma'am. I got your point, ma'am. I mean you're saying that there are a lot of factors which depends.
Yes, I mean, so what I will tell you what we did. We have two projects on metals, one with arsenic and another one with mercury. So what we did, and both of the, and one is a postdoc, another PhD student, that decided that they want to work on MOFs, on metal organic framework. So what we did before we started, and it was different from the arsenic and from the mercury, okay?
Okay, ma'am. Yes, ma'am.
And so we used the different types of ligands, precursors. And what we did, for example, before we started to work on the arsenic, what we did is that we scanned the literature and we subdivided everything into different categories, okay? We subdivided into different categories. So for example, we tested if it's arsenic 3 or 5. We subdivided the papers into pH, into temperature, if there was also pressure. We subdivided it into, just one second. We subdivided it into different categories, and then we scanned into pH, all these things, and then we scanned the table, and we kind of said, okay, and also the reaction time, and
Okay.
then we from that table, and we did the same for arsenic and for mercury before we started to work, because we wanted to see and the efficiency. So we tested everything, and that way we kind of streamed into where we think would be best place to start. Then we examined the raw materials, okay?
Yes.
And after we examined the raw materials, we kind of looked which raw materials would be the best to start with. And that was like our starting point. So what I would suggest is, before starting something, really take time. I know it's laborious, it's annoying, but really take time to search the literature, okay? And okay, so this is something that is very important to do. I would give time for that, okay? I would not undermine that, okay?
It's okay, ma'am. It's okay, ma'am. Thank you, ma'am. Thank you, ma'am.
I would not undermine the pre-work that is needed in order to understand. Okay.
Yes, ma'am.
Please, so, and by the way, we did find different metal organic frameworks for arsenic and for mercury. Okay.
Okay, ma'am. Yes, ma'am.
So, so please consider that it may be different. Which better end-doped? Okay. So there was a question about which is better, end-doped or titanium dioxide. In our case, the end-doped was much better. But it depended on how the nitrogen was introduced to the titanium. So we try to also use degussa titanium dioxide, or we try to actually synthesize the titanium oxide with the doping. The group that did the doping did doping with ammonia. They did doping with melamine, all kinds of stuff, and then they reached to the conclusion which doping was better. But generally speaking, the doping was much better. We had less recombination. We had, we could use UVA visible light, which we could not use with the titanium. So it was really much better. It was, the results were improved considerably. If it can contaminate air, possibly. I'm not an air expert, so I don't know what to say about that. The hydroxyl radicals by themselves are not a problem because the reaction rate with organic material is very high. So the radicals by themselves are not residual in the water. Okay. However, so that is not an issue. However, saying that, hydroxyl radicals tend to form other reactions, okay? So we can have a chain reaction, and that chain reaction may be problematic. In addition to that, hydroxyl radical does not mineralize the pollutants, okay? So we can have, for example, what happened to us in one of the cases, we oxidized a compound that is called velafixine, and we got a byproduct that is considered more toxic, and therefore we needed to increase the reaction process in order to break down also the byproduct that was formed. So that was also one thing that is also required. So that is. Yeah, I would say, yeah, these are most the points that are mostly important. It's very difficult to understand all the small reactions that are happening during AOP. I think that empirical work is the best. I think that AOP has a huge potential, and nano-based AOP has a huge potential. The only thing that we need to do is find a way to move from the design of the materials to working on either membranes or granules or stuff like that. And if we'll be successful, then it will be like an amazing technology. It could be amazing decentralized technology. And this is the most important point, that it doesn't have to require a centralized system. We can design small decentralized nano-based systems, and that is amazing because of their versatility. So I think that's about it for today. Thank you very much, and see you tomorrow. Bye-bye.
Thank you, ma'am. Thank you.
Okay, about the presentations, I need to ask Dr.
Barani. Yeah.
Yeah, whatever Barani was. Forgive me. Whatever he says. Yeah. Okay.
Okay. So let's meet tomorrow morning at 11, right, Professor Ada?
Yeah, sure.
Yeah, as per Indian Standard Time.
Yes. Okay.